assumption that's
Okay. Yeah, 10 minutes ago.
so welcome. So in some cases, we think that the model may fit better, may have a better R squared, for example, if we take these transformed Y. In particular, today, I'm going to talk about 3 specific kinds of transformations that have all been quite popular. The first one, my guess, is most familiar. That's taking the natural log of Y plus a constant, a positive constant, because you cannot obviously take the log of 0, that's not defined. But if you add $1, a penny, even any positive number, then as long as you don't have any negative numbers to begin with, you can take the log of that, okay? So think about taking the natural log of Y plus some constant, perhaps 1. That's one we're going to look at. Second is the inverse hyperbolic sine transformation, which I hadn't heard about until about 4 or 5 years ago. And all of a sudden that became super popular. So if you haven't heard of it, I'll show you formulas, I'll show you graphs, give you a better sense of it, and then eventually explain why you should never use it. But it's the arc sine, or inverse hyperbolic sine, which my guess is you may have seen briefly in like 9th grade geometry and not thought about since. But for a few years it's become very popular because it has some nice properties. And finally, power function transformations or Box-Cox transformations, taking a square root, cube root, nth root of Y. Here, the most popular one has been square root. There are a few papers that have been published that use square root transformations. And so I'm going to talk about those 3 because it turns out all 3 of those have huge problems in a very interesting way if you have zeros. Without zeros, these are all fine. And the problems I talk about today don't apply, but very often we have zeros and then you don't want to do them. And then at the end, I will come back and talk about alternatives, including just vanilla OLS on untransformed Y, 2-part model, Poisson count model. If I remember, I'll also mention generalized linear models. Okay. Let me talk a little bit more about the inverse hyperbolic sine because it's been quite popular. So there are a whole bunch of citations here. In particular, there's a paper by Belmer and Lichtman in 2020 in the Oxford Bulletin of Economics and Statistics. It already has over 1,200 citations. It helped kickstart and popularize inverse hyperbolic sine by pointing out how you can calculate elasticities from that. So elasticity is a percentage change in X leads to a percent change in Y. Sometimes that's the same thing. So anyway, it has become quite popular recently, and I'll show, I haven't shown you the formula for it yet, I'll show it to you in a couple of slides. So here's our contribution. We talk about these 3 kinds of models, log, inverse hyperbolic sine, and power functions, which people use to reduce the skewness. They all technically allow for zeros. You can put 0 into any of those and you'll get reasonable numbers. They all have one additional parameter, C, K, or lambda. And our key insight is that when you use these transformations, the zeros are treated in a bizarrely non-continuous way that causes problems and leads to marginal effects that are not interpretable. And specifically, as you change those parameters, C or K or lambda, we're going to go between 2 extremes. At one extreme, we'll end up basically back with OLS. It's like, why even bother to do the transformation at one extreme of those 3 parameter values? And at the other extreme, we'll end up with a linear probability model that's been rescaled, and therefore you end up with something that's really not interpretable. So this was not known before. I'll show you basically a graphical proof of what's going on. It's a lot more intuitive, although we do have formulas as well. So bottom line, in case you fall asleep, is you do not want to use these popular transformations if you have zeros. It's the zeros that cause the problem. If you don't have zeros, then go ahead. And most researchers who use these end up using values like c equals 1, k equals 1, or the square root function. There's no theoretical basis ever to choose these particular parameter values. And as I'll show, results are very sensitive to which value you choose. So there's no theory, and we're going to end up with, I'll explain this function later, but we're going to end up with marginal effects that are rescaled versions of a linear probability model that are not going to have any real useful meaning. If you end up reading the Bellemare and Wickman paper, they have some examples. We recast their empirical work to show why they get the results they do in their paper. I do want to point out that there was a similar paper published after ours by Chen and Roth. This was parallel discovery. We were all working on this independently. They have a more theoretical paper that basically shows you cannot have one of these kinds of functions that has the following three properties. And as we show, results are sensitive to units of y and so forth. So I do want to point that out. We've had good conversations with them. It's all good. All right. So let me get back to some of the formulas. Again, I'm assuming you know about the natural logarithm and adding a constant to that and how that function works. The inverse hyperbolic sine is the log of ky plus square root of ky squared plus 1. So there's still a log in there, but it's got some interesting things. Let's imagine that y is 0. What happens to that function? So the first term disappears, and then in the square root, all we're left with is 1. So then it would be log of 1, which is 0. So that actually works out very nicely, that you can have y equals 0, and you get a real value. You don't get something loopy. You don't have to add yet another constant or anything. So the inverse hyperbolic sine seems to actually solve the problem of the natural logarithm of having to add a constant. Also, if you look at it carefully, throw in a negative value there, you can show that it's actually symmetric around 0, and you can actually put negative values in, it'll actually work. Anyway, so the inverse hyperbolic sine allows for zeros. K you can think of as like changing the scale between dollars and pennies. So if you have dollars and then if K is 100, that's like having it in pennies. Or if you want to put it in euros or yen or yuan or pick your favorite currency, you can use K to rescale it. It turns out that results are sensitive to K, and unlike untransformed OLS, scale matters. So just to remind you, if you take a data set, you have Y, you run dollars on stuff. If you change it to pennies or change it to any other currency, the final interpretation will be the same, okay? That does not apply if you use the inverse hyperbolic sine transformation, which is part of understanding why this isn't a good idea. The power function, we typically, although it can be any positive number, typically if you want to bring in the right tail, that's going to be a number less than 1. So a half, a third, 1/4, some number less than 1, but positive. And then this at the bottom shows how you can get back to untransformed Y or a linear probability model, sending C to infinity or zero. K does the opposite here, 0 or infinity, lambda going to either 0 or 1. Those are values that will get us one extreme or the other. Okay, a few pictures here. When Y goes from 0 to 5, for different values of C, we get different curves. And as you probably remember, if you add a little itty bitty tiny number to Y, then that curve will asymptotically go down very close, heading down to negative infinity. Power transformation, lambda equals 1 is just a straight line. There's no transformation. This is the square root function. This is lambda equals 0.01, so that's the 100th root. And you can see you get sort of a corner function there almost. And then finally, the inverse hyperbolic sine, as you increase k, we're shifting it up, but we're also getting very steep right at 0, and it's coming down very steeply into 0. Okay, so those are some pictures of what those functions look like. Again, we focus a lot on zeros and how zeros are treated in this paper. And so I'm going to give you a couple of different ways to think about this. If you like derivatives, one way of thinking about what happens is that the derivative of these functions get wonky at 0. So this just shows for the first two, log of y and inverse hyperbolic sine, that if you take the derivative at y equals 0 and either send c towards 0 or k off to infinity, you get infinite slopes, as we saw in the previous pictures.
So what you're sort of saying is if you're shrinking y down to 0, as you go from 1 to 9/10 to 1/10 to 1/100th, you're getting this vast stretching.
Exactly.
And maybe even more than the ratio would suggest.
Yes, that's exactly right. I'll show you pictures, but that is the right intuition. Okay, so good, hang on to that. And what it's gonna do visually is separate out the zeros. I'm not gonna spend much time on this slide. This shows how to do retransformations. We're not, unless anyone's, yeah.
Pardon me, the point about taking k to infinity here was where you were getting the asymptotic results, and that's why you were doing that in that.
Yes.
The derivatives at 0.
Yes.
I mean, I know the arc cinch has at 0 itself has a finite derivative, but not with k going to infinity. So, but with that, yes,
Yes.
yeah. So I am okay. Thank you.
Okay. I'm not really going to talk about the retransformation, and there's some odd issues there. So just summary of where we've gotten so far. We have outcomes that are possibly 0, skewed positive values typically. We want to bring in the right tail, perhaps make the positives closer to a normal symmetric distribution, but still allowing for zeros. Yet we want to report results on an untransformed scale. And our paper talks about how the zeros are treated differently by these functions than the positives. And the bottom bolded quote is something that John wrote, and I just love this sentence. Whether or not 0 is conceptually special, it does not follow that performing algebraic gymnastics to accommodate it analytically is helpful in credibly estimating parameters like marginal effects. Okay. I'm going to go to an example with real data, and then that will allow us to show pictures of what's going on and how the zeros are getting separated. So we're going to use data from the Medical Expenditure Panel Survey, also known as the MAPS. We have data over 7 years, over 130,000 observations, non-elderly adults. It's the dependent variable is the total annual healthcare expenditures. So about a quarter of the values are zero. A lot of people don't spend any money on healthcare in a typical year. The mean value is just under 5,000 and the median, because it's highly skewed, is a little over 1,200. Okay, so that gives you some sense of the data. Here's a histogram where we have taken everything. I mean, this goes way into the, probably outside the building. We've summed it up here. So we have 11,000 that have at least 10,000, just so you can see what's going on here. There are 32, so it's actually 24% are actually zero. The first bar has like zeros of the people who spend a few dollars. So that's why it's more than 24%. Okay, so you have a highly skewed positive distribution here, as well as a significant fraction of zero. So this is sort of a classic case. We have a few covariates. Average age is 40. Roughly half are female. Average family income is about 60,000. Any limitations means physical limitations, so that's about 20%. And these physical and mental health scores in theory range from 0 to 100. In practice, it's more like 20 to 70. Higher is better, and the mean is 50. Okay, so higher is better is the important thing to remember. Yeah, 133,000. Okay, so here's the money slide. This is what you want to remember. Go to the middle where it says ln y plus 1. So hopefully that's obvious. That's the log of y plus 1. And on that, the sort of pale green, if y is equal to 0, you add 1, then take the log, that takes you back to 0. That's why the left part of that distribution is exactly at 0, the log y plus 1. Then the positives on this box plot, you can see where the median is, retransformed, kind of see what the spread of values is there, right? Now, I'm going to progressively add smaller and smaller values of C, and we'll work our way up the graph. We're going to add 0.1, 0.001, 0.001, 0.001. Each time we do that, when y is actually 0, we're going to take the log of a smaller and smaller and smaller number, and those go off to negative infinity. So as we add smaller numbers, the zeros get separated out. Okay. Meanwhile, when we add a little tiny number, we're effectively not changing any of the positives. If you spend $10,000 and I add 0.001 to that, and then it just doesn't matter, right? So we're not changing the positive distribution, but adding a tiny number sends the zeros off there. So what it's doing is it's separating the zeros from the positives. What happens as we go out here, in particular here? Well, when you add a large amount and then take the log, it's really hard to see, but if we got out a microscope and looked at this distribution, it would look remarkably like this, okay? Except this part wouldn't be bunched up here, but it would, this is actually a very highly skewed distribution, just crunched up because it's all logged. And that's what happens if you add a gazillion dollars to actual spending and then take the log. So in other words, when you add a huge amount and then take the log, the underlying distribution is basically what you started with, just compressed a little bit. And then if you do the inverse f function, you get back to where you started, effectively. So this is like doing a whole lot of work for nothing. Effectively, we'll get back to OLS. And what's going on up there is almost like a linear probability model. We have zeros and we have positives with a little bit of noise. And that's the fundamental insight. We do the same thing for the inverse hyperbolic sine, except K here has sort of the opposite effect. As we add bigger and bigger values of K, that's where the slope got really steep. And it's, in this case, we separate the zeros from the positives. And so if you multiply by, you go from dollars to pennies to Italian lira in the 80s to, was it Zimbabwe? Zimbabwe had
Dollars.
was it dollars? They had just unbelievably large inflation. We take the positives and we send them off here. This looks like the original distribution though, right? All we're doing is separating out the zeros. If we go the other way and multiply by a really tiny number, we're gonna compress things down. But again, if we got out a microscope and looked at that green distribution, that's gonna look like the original OLS distribution almost. Okay, so in one direction, we're getting back OLS, and here we're getting zeros versus positives with a little bit of noise.
Are you just painting the head, the bright tail on more on the orange curve? The smear, the second one, the top orange?
Oh, the top one?
Yeah, the second from the top.
Yeah.
That, I'm wondering about the additional smear cloud, if you're just emphasizing that tail in that picture. Or is it somehow different?
This is what's automatically produced. I didn't run this through a photo editor.
1.5 times IQR.
Yeah.
That's,
So I think if we had intermediate numbers between the first two, you would see more and more tail starting to pull out, as well as getting compressed. That's why you need a microscope to look at the green one.
Okay,
But there will be more and more of a tail getting pulled out. So
I see.
in the inverse hyperbolic sine function, when you multiply by a little tiny number, again, you're effectively undoing the curvature, and you're getting back, when K gets small, we're moving down this curve and it's getting flatter and flatter, and then why bother, okay? Okay. Similar things happen also with the power function, but they're hard to retransform, so we didn't do as much with that. All right, so linear probability model, I hope you're all familiar with. It's running an OLS regression when the dependent variable is either 0 or 1. And what we show is that if you actually run a linear probability model, 0 versus positive, you get beta LPM. What you get with these transformations, beta of some transformation, is sort of, you can get arbitrarily close to beta LPM times a rescaling factor. What's the rescaling factor? In this case, it would be the distance between here and something about here, roughly the median value of the transformed value of this. And with log, it would be the difference between like minus 20 and, I don't know, 6 or 7, okay? And so that would, you put in those two values of function at 0 and roughly function at the median value, middle value of y, that's going to rescale the LPM value, and that's going to get you the beta. It's not what you want. That has no real meaning, okay? So, but that is what you get, and therefore, the betas that you get from the transformed values are somewhere between these rescaled linear probability models and untransformed OLS. Here's another way of expressing it. Down in this corner, we have, let's see, we're just regressing expenditures on a single variable age, a single continuous variable age. Here's the linear probability model for binary. Did you spend anything versus nothing? And we see that there's a positive slope for age. And then we've also done it for 3 different values of constant term. When the constant term is 1, there's a lot of spread in the positives. When it's 0.001, there's less spread. When it's 0.001, there's less and less spread. You can see that if we keep adding a smaller and smaller value, we'll just shrink this noise down to 0 in the limit, and we'll end up with this. So this is sort of another visual proof. We have already rescaled this, so this is already 0 to 1 instead of 2 other values that don't make sense. But it's just showing why there's this relationship when you have the zeros separated out from everything else. Same kinds of pictures for the inverse hyperbolic sine, but here instead of sending c towards 0, we send k towards infinity, but we get the same kind of squishing of the positive values and separation. Okay. All right, so now let's actually run some regressions and I'll show you what these coefficients do when we have constant terms c that we add to the log, or we have k of different values. If you can memorize a couple of numbers from this table, this will be useful. This is a simple OLS regression of annual expenditures on a few covariates. So just to walk you through it, the older we get, the more we spend on average. Probably not news. For a non-elderly adult population, women on average spend more. Families with higher income spend more. Those who have any limitations are worse physical health, they spend more. As physical and mental health scores go up, that's better health, and spending goes down, okay? So just the signs of all of those make sense. And if we run a similar linear probability model, 0 versus 1, did you spend anything? Yes, or nothing, 0. All of the signs are in the same direction. Of course, the numbers are very small because it's only pushing the probabilities a very small amount, okay? Any questions on that? Memorize a couple of the numbers because we're going to benchmark off of this.
The untransformed y in dollars or some other?
Yes, so yes, thank you. So it's dollars is the unit. So specifically then every year of age, at least in this data set, controlling for everything else, is $37 more per year. So $370 more per decade on average. Okay. All right. So here we have a couple, so every column is a regression. Red is bad, blue is good. So when we do log of y plus a really big number, I said that would get us back to OLS. These are marginal effects after doing a retransformation, which I haven't really told you how that works, but we're getting numbers, okay, it wasn't $37, it was 38. That's pretty close. Was it 654 something for women? This is 677, so that's fairly close. As we move over to log of y plus 1, we're getting progressively weirder numbers. These are just out of line, okay? I know we spend more on average as we get older, but we don't spend $500+ more per year, every year, year after year. That's out of line. And then going in the other direction, so this was the red column on the previous slide. Then we're getting worse and worse as we add smaller and smaller. So things just get totally out of control as we add smaller and smaller constant terms. So you want to go, the only way to get sensible numbers with the log is to add a constant that's so big that we're undoing the logginess of the transformation. Similar idea here with the inverse hyperbolic sine. This has a k value of 1. We're getting really big numbers compared to inverse hyperbolic sine when you multiply by a really tiny number. But again, this is undoing the whole point of that. So we're getting numbers out of line.
So what about the second column?
Well, it's in between. So
Yeah.
this
Sure.
column,
Is there some benefit, you know, if the goal is to reproduce OLS, then do OLS.
exactly.
But
That's
what
exactly
if you
right.
don't wanna do OLS? Is there a reason to think that blue column is better than the one next to it, other than it's further from the OLS solution?
So we'll talk about other solutions at the end, but hopefully the point here is, oh no, I mean, because I'm pretty darn sure no one has ever published a paper and said, I'm gonna use a k value of 0.001. Because, like, why would you do that, right? So when people use inverse hyperbolic sine, they use k equals 1, because why not? And so,
Cause it's in red.
because it's red as okay, and then going the other way, which gets ridiculous, again, nobody actually does this, but it just to show you that you get values that are really good. Okay, then this shows similarly values for the linear probability model. And we get numbers that are a little off from there. They're not as ridiculous. They're sort of in the same ballpark, but they're all a little bit too big. But instead, if we do log of y plus an enormous number, or sorry, that should be log of y plus 1 over Google. That should be a tiny value. No, sorry, it's the other way around. So that's correct. This should be 1 over Google times y. That'll get us the right thing. Then we can get linear probability. We can reproduce linear probability models as close as we want. Okay. So again, the point here is with real data, we can play around with these constants. We see we get different values. That should be a little concerning because there's no theoretical reason to do that. And so, okay, so we have a problem. When you have zeros and you do any of these transformations, it changes the marginal effects of coefficients a lot. And it's really not clear what to do. So up to this point of the paper, the bottom line is don't use these transformations if you have zeros. If you don't have zeros, that's fine. Go ahead and take the log. You don't have to add a constant, just take the log. There are reasons to do that, pulls in the right tail. You can interpret it as elasticity or semi-elasticity. There are lots of good reasons to do that. But if you have zeros, then you don't want to do this. Right? That's what's causing the problems. So there's several alternatives. One is you may just want to run good old OLS. And if you have covariates that are highly continuous, you may want to break those up or do splines or something else. But untransformed Y is a possibility to at least consider. Two-part models, which were invented basically in the Rand health insurance experiment by Will Manning, Joe Newhouse, and others. As the name implies, there are two parts. So the first part is you predict, do you have a positive value or do you have a zero? And you do like a logit or probit for that. And then on the subset of data that has a positive value, so okay, now we've got rid of the zeros, then you do perhaps OLS or generalized linear model or log of y, or you do something else, but you get rid of the zeros, and then there are ways of putting it all back together again and figuring out overall marginal effects. So this is a well-known model in health economics. That would be my go-to way to deal with this. If I had to pick one without looking at the data, I would go to two-part model. In part because it's often interesting to look at each part separately. What covariates predict any spending and which covariates predict the amount of spending. Sometimes you get different results. Poisson count model works remarkably well. I see a no.
It's not count data.
It's not count data. So, okay.
Sorry, what?
Mine is count data.
Yeah, that's right. Give me the money.
Yeah,
Okay.
but there should be a zero inflated negative binomial choice.
No, you really don't want to do that.
No, I do.
No, you don't.
No, I really,
No, you don't.
it's very much like the two-part model.
Except that it's not well identified.
No, it is.
No, it's not. So, but
It is.
that's a topic for another night. We're gonna stay away from that.
That'll be for a November meeting.
I do want to come back to the Poisson versus the negative binomial versus not doing them at all. Like 5 years ago, I would have been shaking my head also, okay? And because it's not like so let's think about dollars annual expenditures. It's not count data. It's not remotely count data. It's not bunched up in the way that you want count data to be with zeros and then ones and then twos and then threes and so forth. I get that. Jeff Wooldridge, who's a famous econometrician at Michigan State, has for years been saying how wonderful Poisson is and how robust it is to deviations from the basic count thing. And even when the variance is bigger than the mean instead of equal, and every time I took actual count data and looked at Poisson and negative binomial always did better in any sort of reasonable way. They often got similar marginal effects, but sort of fit of the data, negative binomial always better. In this sort of situation where we're starting with data that are truly non-count, I will give you that. It works remarkably well. It actually does. So
Why don't you just skip to the GLM with the log link? I mean, the Poisson model has the log link, and I feel like that's the main reason.
So GLM is interesting because that plays around with our expectations. It's a joke. So what we do when you take the log model is first take the log, then model the expected value of the log. What GLM does is it first takes the expected value and then it logs that basically. The order of operations matters, whether you log or take the expected, because it's nonlinear, so order of operations is going to matter. And functionally what it means is if you have like 2 or 3% of your data are zero, you're mostly positive, I get a few people that don't spend anything. Doing the log transformation won't work, the reasons we talked about, but GLM probably will, because when you take the expected value, if you only have a very few zeros, the expected value for everybody is going to be positive. And so you can do GLM sometimes with few zeros because the expected value for everybody is positive, and then when you log it, you're fine. So GLM may work, but if you have, I don't know, 20%, 50% zero, like I don't think that would work in practice. You end up with the same issues. So I will show you a few results now that use Poisson that get remarkably similar answers to OLS with these real data. So I invite you to go home and play around with Poisson on non-count data. And I have been transformed by Jeff Wooldridge's comments and suggestions on this, and I now, for non-count data, Poisson is something I would consider doing, and it does pull in the right value. So that's my comment on that.
Well, I think it acts a lot like count data because the higher the mean, the higher variance in spending. And that's a very, very count-oriented behavior, and your data showed that with the skewness.
Right, the Poisson fundamentally assumes that the mean and variance are
But
equal.
I'm still stuck on my zero inflated negative binomial.
Okay,
That's my
let me come back to that. Brandy, you got a comment?
Yeah, have you looked into using gamma regression?
Have not. So there may be other things that would work here, but this is a pretty good list to get going. With other possibilities, and depending on the distribution and your research question and what you're trying to do, some things may work better. The problem with the zero inflated, it is identified, it's just not well identified in my experience.
I can tell you the way what reason I think it's extremely well suited for this. You've shown us data where there's a lot of people who have zero expenditures, your zero inflation, right? And the way the zero inflated negative binomial model approaches this is to think of that as a mixture, just like your Bilotti et al. People are doing.
Correct.
And the zero model is modeling the probability of being non-susceptible to cost.
Right.
And we'll have different coefficients, which your Bilotti people also appreciate, that they have different potential effects on covariates on causing zero costs. Versus of the people who are susceptible to generating costs because they were in a more, whatever, frail state for healthcare expenditures. You are able to model amongst the susceptibles what drives up cost. And it's very similar to the two-part model, except that it thinks of it as a mixture where even if you're in the susceptible to generating costs, you can still have a zero cost.
That is correct, yes. In my experience, and
it always does better than negative binomial when you have inflated zeros, always.
By the way, they may not be able to hear you on the Zoom meeting.
Okay, well,
They should come.
what?
There you go.
Yeah,
Yeah, I said it.
or we could just get the two screens with two different people in November and have a duel.
I think they-
So I will say it's been many years since I looked at the zero inflated Poisson or zero inflated negative binomial. Because what I remember is them being very sensitive to seemingly small changes in the data or in the right-hand side specification in a way that the other models were not.
well,
That's what I remember, so
I look at
you
your-
may be right.
I look at your data where you're using ordinary least squares, and it's the ordinary least squares that's causing the predictions to go down towards zero as you change where the zeros are with your plus constant. And with the skewed data, it's not homoscedastic by any means from what I looked at. So I think you're already working from a disadvantage, assuming a linear model with homoscedasticity, when your data really did look like a count distribution with the skewness. So that's just my opinion.
Something to consider. I should go back and look at the zero inflated models again. As I said, it's been a long time, so you undoubtedly know a lot more about them than I do, but my memory is that they seemed very sensitive to small changes.
Well, you don't have to
Some-
transform the zeros, so you don't have those small changes.
what I meant is in right-hand side variables, adding or subtracting variables, just to see how things change, or if you change your data in seemingly small ways, the convergence. Anyway, we're getting way off topic here. This is very interesting.
It's not as bad as you recall.
Okay.
I would state
All right.
confidently.
I mean, how
So
could you know that though? Because you don't have access to the same data. I mean, I feel like you're really making strong statements, but
Well,
it could fit it better, it might not.
I've compared them when teaching, because I teach these models too, so.
Yeah, but teaching, you don't have access to all the data.
But I use them on data sets, I'm not just teaching theory, I'm
Right, there's could be
analyzing
different
COP
things.
exacerbation
There could
data.
be different fits for different models. I'm just saying you're like stating some things you might not really know.
What I would suggest is that we get on with the presentation.
Yeah.
And by the way, it's also of interest to me, I started to do it one way, I started to do another way here. Adding small constants to the log was what I thought you should do. And then you'd find out what level of small constant gave you a stabilized result. It turns out it seems to be like bleeding the patient.
Well, you're
And
doing
I've also-
ordinary least squares, so you've got these residuals.
So I think what we ought to do is, we want to have a session on this later to cover this.
So here are some alternatives. I'll leave it at that. And in order to show whether these alternatives did well or not, we simulated data, so we knew what the answer was. And we set this up with the data generating process was two-part model, so there was a process for which we got positives, and then if there were positives, then we had values that were either normal or skewed. We did it both ways. We had a range of probability of having 0 from 5%, 30%, 80%. So we did this a variety of different ways. We did not do the zero inflated, but we did do two-part untransformed y and Poisson, and then compared them with the log and inverse hyperbolic sine. Given the data generating process, we believe that this should be very close to the truth. And you'll see that untransformed, so the notation here is TPM is two-part model, n is normally distributed for the positives, and 0.5 means 5% of the data are zeros. This is untransformed y and Poisson. Those are all very similar for marginal effects. Log y and inverse hyperbolic sine are way off. We have more of these where this is up to 30% zero, 80% zero. So we're getting, these are in the same ballpark. I will say, though, that the data generating process is pretty nice. Whereas with a lot of real data that is very skewed, you may run into other problems. Okay, so this is kind of nice simulated data in a way that may be a little too optimistic, but these three seem to do like well, and the others, as we expected, are way off. I'm gonna go through the next couple slides quickly, because if you haven't read the Bellemare and Wickman paper, what I'm about to show you may not resonate. Again, their paper, super highly cited. They had some real data, and they, as well as simulated data, and they did a number of things. For one of their simulated things doing elasticities, they actually had a data set with no zeros. So things worked out very nicely because they didn't have the problem that is the real, again, inverse hyperbolic sine with no zeros works very well. But then they also took real data about a work demonstration. So there was a retraining program, 30% zeros. They run a bunch of different models, including inverse hyperbolic sine, and they get different results. And they say, we get different results, but we like inverse hyperbolic sine, so we're gonna go with that. We we rerun everything and show that the reason we get different results was the results are very sensitive to K. So and we show that if you change K or estimate it in other ways, then you get more reasonable results. Same kind of picture, but with their data, just showing relationship between these. Anyway, so getting back to sort of the bottom line, what we would suggest is instead of sort of knee-jerk reaction of, oh, I have skewed data, therefore I should definitely retransform the data, the dependent variable. So the default should be, well, maybe not. And there may be reasons to transform the dependent variable, particularly if you don't have any zeros. But it's not at all clear that we should just be transforming the dependent variable as the sort of current status quo. And then we'd be better off thinking about this a lot more and seeking alternatives. So conclusion, 3 popular transformations, log of y, inverse hyperbolic sine, and power functions. The zeros are treated in a very non-continuous way, very sensitive to the 3 parameters. And having zeros will distort the estimated coefficients and therefore the marginal effects on various variables. And in particular, the marginal effects can sometimes be related or going in the direction of this very odd rescaled linear probability model. And so please don't use these models when you have zeros. And consider other models without. So here are a bunch of references that I referred to, including our paper, which, as I said, came out earlier in the Oxford Bulletin. So that's what I have. Thank you very much for coming tonight.
I think this may have been the most important talk I've seen in 2 or 3 years.
Wow.
The last one was Jeremy Albright's work on causal inference, which could be summed up as everything you've been told to do in regression about causality is wrong, and this is what you should do. Because we all have these things, and I think everyone has their favorite one. Because again, I was taught that in a sense, take the log of y plus a constant, shrink the constant down until the marginal effects stop changing, and there you've got the best answer, which again looks to be like, put bigger and bigger leeches on the guy until he stops complaining. You like you like the negative binomial.
Virulently.
Virulently. And then he's pointing out in some cases that's well identified.
Let me.
Okay, sorry.
That's my memory from a long time ago. It's been a long time. So
Okay.
let's just leave that as another possibility to consider.
I will say that the one kind of disadvantage of these mixture models where you model 2 different components separately is that software doesn't necessarily give you the prediction back. It'll give you the parameters from the different models. And the typical user doesn't know how to combine those results from mixture distributions, and the software doesn't do it for you. They could if they just program the theory around it. But if you're really trying to predict cost, and that was your main goal, you have to have someone who knows how to put back together the story from the 2 parts into some kind of prediction that's intelligent. And so the lay user won't know how to do that. And that might make you want to use a Poisson model where, well, there's only one fix for the Poisson model. There's that little, what do they call that thing? The inflation factor or something that they multiply by the variance term. There's some fee that they use in SAS. I can't remember what they call it. Is it the inflation factor or?
Variance inflation.
Variance inflation, something like that, yeah, they, so it'll let you get closer to, you know, not assuming mean equals variance. And you don't have to think it's hard to make a prediction, but that also doesn't deal with the excess zeros. You really have to have a mixture model, the model of the zeros separately, in my opinion, to get an answer to this story.
Right. So if I can expand on that, because I agree with you. Taking something like the 2-part model, there are three kinds of effects one might be interested in. So for example, what is the effective age on the probability of any expenditures? That's the first part. What is the effective age on the amount of expenditures if you spend anything? And then what's the overall effective age combining both of those? The Bellotti et al. Paper both shows how to combine and has Stata code and a Stata package that does exactly what you were asking for Stata users, allowing you to look at the first stage, the second stage, or the combination.
And did they, for their two-part model, are they assuming ordinary least squares for the part?
There are a variety of options. So you can do GLM, logit or probe at first stage, ordinary least squares.
So they would allow
Right.
something like
Yes, for the
Count
positives,
distribution.
yes. Again, depending on the
That's
data.
why not, if that software is available, I would say that probably would be the most attractive approach, because SAS, these zero planar negative binomial models, they just give you the betas and the inference on the betas.
Yeah.
They don't do the estimation for prediction for you. And I don't think the standard user knows how to do that. So if this other Stata package does that, I think that probably would win any game here.
Yeah, so that we published in Stata Journal almost a decade ago. But it does allow for different options for both the first and second parts. Back to them. Good. Other questions, comments, complaints?
Thanks for very
Credit is due.
interesting.
You can just page through these, I can pause them during the recap. I think you were probably 4 or 5 slides in, but.
Oh, yeah,
I don't need you to go through everything, I just need you to show the slides. Like back to the first 2 or 3 slides, just to get them on the recording, and then I'll
Completion.
put them back at the beginning.
That's where you.
Excellent, thank you very much.
Sure.
I'll stop the recording.
Well, thank you very much.
Sure.
Again, that was